A planet where it literally rains glass, sideways, at 7,000 kilometers per hour, is not science fiction. It is a real world we've detected orbiting a star 63 light-years away. Astronomers call it HD 1893330b, a hot Jupiter with winds so fast they could circle Earth in minutes. And it is just one of thousands of exoplanets, planets beyond our solar system, that are redefining what we even mean by the word planet. We used to think of planets as mostly familiar, rocky worlds like Earth and Mars, or gas giants like Jupiter and Saturn. But as our telescopes have improved, we found worlds so dense they crush rock into exotic minerals, so hot their surfaces might be oceans of vaporized metal, and so extreme they orbit their stars in less time than it takes you to binge a TV series. In this chapter, we're going to pin down what makes a planet extreme and meet the main classes of alien worlds that push physics, chemistry, and sometimes our intuition right to the edge. To talk about extreme planets, we first need a baseline. What actually counts as a planet? In modern astronomy, a planet is a body that orbits a star, is massive enough that its own gravity pulls it into a roughly spherical shape, and isn't massive enough to ignite sustained nuclear fusion in its core. That's what separates planets from stars and brown dwarfs. Within that broad category, extreme doesn't have a single official definition. Instead, astronomers look for outliers, worlds that sit on the edges or beyond the edges of known distributions in properties like temperature, density, orbit, and composition. If you plotted all known exoplanets on a giant, multidimensional graph, extreme planets are the points way out in the tails of the curves, the weird ones that force us to revise our models of how planets form and evolve. Let's start with perhaps the clearest kind of extremeness: temperature. Take Kelt 9b, more than 670 light-years away. This planet orbits so close to its star that it completes a full orbit in just about 36 hours. Its dayside temperature is over 4,000 degrees Celsius, hotter than some small stars called red dwarfs. At those temperatures, molecules cannot remain intact. The heat tears them apart into individual atoms. Even metals like iron and titanium are vaporized into gas in its atmosphere. This is a gas giant, roughly Jupiter's mass, but nothing like the chilly, banded world we know. Instead, it's more like a puffed-up drop of stellar atmosphere, superheated and distorted by its star's gravity and radiation. Why does Kelt 9b get so hot? The key is proximity and stellar type. It orbits an A-type star, much more massive, larger, and hotter than our Sun, with a surface temperature around 10,000 degrees Celsius. The planet's orbital distance is only a few stellar radii, closer than Mercury is to the Sun by a large factor, so it is bathed in an intense flux of ultraviolet and visible radiation. The energy per square meter hitting its atmosphere is thousands of times what Earth receives. At that level, not only is the upper atmosphere heated, it is literally being boiled off into space. Observations show that Kelt 9b is losing its atmosphere atom by atom in a process called hydrodynamic escape. The gas is so hot that it behaves more like a fluid jetting away than a gentle evaporation. On the other end of the thermometer, there are planets that are extreme because they are incredibly cold. For instance, some exoplanets orbit faint, cool stars far from their warmth, or have very wide orbits that take hundreds of years to complete. A planet like OGLE 205 BLG 390 LB, yes, the names are terrible, is thought to be a super-Earth with a mass about 5 times that of our planet, orbiting a dim red dwarf star at a distance roughly similar to the asteroid belt in our solar system. Its equilibrium temperature is estimated around -220 degrees Celsius. At those temperatures, even nitrogen and oxygen, the main components of Earth's atmosphere, would be frozen solid. Any water there wouldn't just be ice, it would be a rock-hard mineral, part of the crust. But temperature is only one axis of extremeness. Another is density. How much mass is packed into how much volume? Consider the exoplanet called Kepler 10b. It was one of the first confirmed rocky exoplanets, and remains one of the densest. It has a mass about 3.3 times that of Earth, but only 1.47 times Earth's radius. That works out to an average density of about 8.8 grams per cubic centimeter, nearly twice Earth's density, and even denser than pure iron under normal conditions. This tells us its internal structure is dominated by a massive iron core with only a relatively thin silicate mantle. In other words, it's like taking Earth's metallic core, supersizing it, and then wrapping just a small layer of rock around it. At the surface, gravity would be more than twice what you feel on Earth. Every kilogram of you would feel like more than 2 kilograms. Climbing stairs would be a serious workout. On the opposite extreme, some planets are so puffy and low density, they behave more like tenuous clouds than solid worlds. WASP 107b, for example, has a mass only about 12% that of Jupiter, roughly comparable to Neptune, but it's almost as large in radius as Jupiter itself. Its average density is around zero point 0.3 grams per cubic centimeter. That's less than the density of cork, and much less than water. If you could put this planet into a giant cosmic ocean, ignoring all the other physics that would go horribly wrong, it would float. How does a planet get that fluffy? Heating from its star and the way gas giants accumulate and cool. The intense stellar irradiation puffs up its atmosphere, and because its core mass is relatively small, the gas is not held as tightly, resulting in a very extended, low-density envelope. Orbit can also be taken to extremes. Ultra-short period planets are worlds that orbit their stars in less than a single Earth day. One of the champions is the planet designated 55 Cancri e. It circles its star at a distance about 25 times closer than Mercury is to the Sun, completing an orbit in roughly 18 hours. At that distance, tidal forces, the difference in gravitational pull between the star-facing side and the far side, are so strong that the planet is very likely tidally locked. This means one hemisphere permanently faces the star, baked by constant radiation, while the opposite hemisphere is in eternal night. Observations of its thermal emission suggest a dayside temperature of around 2,400 degrees Celsius, while the night side might be somewhat cooler, but still well above the melting point of many silicates. Some models propose that the dayside could be covered by a global ocean of molten lava, with the night side crust solidifying, but periodically resurfaced by flows of magma. Some of the most dramatic